Thank you, Marco. Hello, everyone. Good afternoon. Hoping everyone is listening loud and clear. It seems that some of you are having some problems. So let's start first by checking where everyone comes from. Could you please use the drawing toolbar and put a mark in the place where you are? Okay, thank you so much. So let's move on. So over the past days, Europe has been dominated by a block pattern, which means a stationary pattern with some interesting weather events. Before showing you the weather charts for today, let's have a quick look over some social media posts. So the record-breaking high-pressure system in Northwest Europe brought warm weather over Northern Europe and Scandinavia, and also severe weather with the cutoff low, severe weather over Spain. We had also some cyclogenesis over Northwest Atlantic that caused a record snowstorm in Newfoundland. So some busy, these last days were some kind of busy days with some interesting weather events. So the storm Gloria over Spain caused severe damages with rain, snow, and waves, and also with a significant wave height breaking records in Valencia buoy. We have to go back on 31st January 1911 to have 8 meters record. So the Valencia buoy is here, where is the arrow, and we have 8.44 meters. And there was a storm in 1911 that was record 8 meters. So big waves in southeast Spain. So the storm surge also caused, the storm surge caused by this storm can be seen with this before and after Sentinel-1 radar image from Elba Delta, which is quite impressive. So the first image is on 15 January, and the second image is from 21st January. So it's quite impressive, the area of the impact of the storm surge. So just to remember, for those of you who doesn't know, the Ebro Delta is in here, southeast of Spain. So this kind of block pattern is known by the Rex block and is defined by a high pressure system located polewards of a low pressure system. When it is a persistent block, of course, this area experiences dry conditions and this area experiences rainy conditions. And sometimes, as I said, if it is persistent, this can have these areas can have flooding and severe weather in this region. Of course, there are other block patterns, the omega block and the blocking high. You can also see this web page, and it's really simple basics, and you can learn more about these kind of patterns. So let's check an overview of Europe with the warnings. So we see here that we have mostly yellow warnings. This area, Central and Eastern Europe, windy, and we have also in this area we have some fog warnings. Still in these parts of Spain and France, because of the cutoff low, we still have some orange and red warnings for flooding, mainly for flooding. when this has started, so we have on 18 January an Atlantic trough approach Western Europe and cross Iberia. See this area here, cross Iberia, and stayed here for some days. The high pressure system over British Isles started to build up and became an intense high. And these two systems have been almost stationary since 18 January. So today, this is from today at 6 UTC. Finally, the high pressure system, it is like here, the high pressure system is weakening and the cutoff flow is still active and moved westward, bringing now some unsettled weather over Portugal. So this is the area of the cutoff flow. Here in Portugal, we are not expecting as severe weather as in Spain, but some showers, possible hail, and snow are forecasted for some areas of Portugal. This image also shows, here, this image also shows some frontal cloudiness over here, moving over the Atlantic towards northern Europe, some deep cyclone north of Iceland, and another deep trough can be found far east in this area, with strong winds behind the cold front. So you can see this area with strong winds, and there are some yellow warnings for these regions because of windy day. The central and Mediterranean, the central Mediterranean is under the influence of the trough, the European trough. South of Azores, we have a low pressure system that has been quite stationary. We cannot really see it from this image, but it has some cloudiness, convective cloudiness, and we have some warnings from for aviation. So in this image, we can see the 300 hectopascal height. You see that the cutoff low is more or less dominating, with also the trough. And the Rex blocks is becoming less strong. The typical pattern is less easy to recognize. So we have the reach over here, and it's not as intense as it was in the previous days. Also, we have the dry stratospheric air that acts as a tracer to identify PV anomalies, which can be seen in this area, the deep trough over Eastern Europe, and also in this area here, in the near Newfoundland. So these areas have some kind of PV anomaly, so we have some expect some activity in this region. We also have some kind of in this area also, and this area also. So this is important to see where it might have some cyclogenesis or activity, convection. So these are some areas that we have to pay attention. So also the jet stream at 300 hectopascal very well identifies the cutoff flow and the deep trough. So here, of course, and the deep trough, it's really well defined. Looking at tonight microphysics RGB, so we have some parts of Europe we still can use at 6 UTC, we still can use the night microphysics. There are other parts of Europe that we cannot use the night microphysics because it's already day. So we have the HRV clouds RGB. We see here some fog and low-level clouds, and also in some places here and here, some places over Iberia, we have some low clouds and possible fog. So the appearance of low-level clouds and fog in the night microphysics can change a lot, and this depends on the transparency of the cloud fog layer. So if it is a thick layer or a thin layer, more contribution of the green beam, and if the thinner the low cloud, the smaller green contribution. So here you can see you have lots of different shades, and also here you have different shades of the pinkish, whitish, and also some greenish. So it depends a lot of the transparency of the cloud. But not only, it depends also of the cloud fog microphysics properties. So we are dealing mostly with water clouds, and we can have large particles and small particles. So it's another reason that we have some kind of different appearances of this kind of cloudiness. Also depends on land surface temperature and cloud top temperature. So this is more the blue beam and the contribution for the 10.8. So these are the main reasons that we sometimes have different appearances or different colors within these areas of low-level clouds or fog. So to sum up, here are some conceptual models for today. So the frontal cloudiness over northwestern Atlantic, we have a warm front band, we have the cold front, and a front type. We also have some open and closed cells convection here. We have a coma near Iceland. Warm front band, warm front shield, and this area of fog low stratus, and of course we have the cutoff low. So not busy weather, not many things, but of course we have several systems here that are going to move eastwards and affecting Europe in the next days, because the block pattern will change to a more zonal pattern. So just to finish my presentation, the cutoff low near Spain also helped bringing dust from Northern Africa. Here we can see the ensemble model from CAMS from the 21st January at 0 UTC. This is a T minus 24 hours. And you can see the forecasts of dust in this area of Northern Africa. If you see for the same hour, for the same time, so 0 UTC, 21st January, this is the dust RGB. Do you think it shows dust? Can you mark where it is? Yes, Very well. Yes. You are experts. Thank you so much. So for today, the same model. It's for today at 6 UTC, and it's the same run. You can see that the spreading north in all this area, and the dust RGB. The dust RGB shows some hints of dust, but not as clear as on the other image. So we have some hints of dust in this area over here. So to sum up, just to remember some hints how to use the dust RGB to detect dust. So here you have the channels that are used in dust RGB. The dust, as you marked so well, is magenta. So we are expecting a strong signal in the red and blue beams. So the brightest temperature between 12 and 10.8. So this one here, smooth. So this one is positive for dust clouds. So there is a high red contribution. So you can see here the positive difference between these two channels. The brightest temperature between 10.8 and 8.7 is small for dust. So we have a low contribution for the green beam. The 10.8 alone on the blue beam is important to distinguish night and day and the level of the dust cloud. So it's important to know what is the temperature of the cloud top. So less contribution of blue means that the suspended particles are cooler and appears purple. So just a quick reminder for this use, so you can use the dust RGB. If you want to learn more about the dust RGB, there are several resources on the EUMeTrain webpage. But this information, I took it from the operational use of RGBs part 1. So thank you. Now I'm going to pass to my colleague Bruno. It's time to change the presenter.
So, hi everybody. Good afternoon. I'm going to go a little bit back to December 2019, just to show you that. During December, we had the Portugal mainland was affected by a western flux originated by some lows that were in the North Atlantic, in the high latitudes of the North Atlantic, and high pressure systems south of Azores and Madeira. And you can see the RGB, the air mass for the 20th of December, and you can see this flux. This western flux. So the lows didn't affect directly Portugal, but we had this high moisture air mass and hot air mass that was here during several days of December. And this up here you can see the geopotential for 500 hectopascal, and you see the western flux at 500 hectopascal. So this what happened was that we had persistent rain and strong winds during several days, and we had prior to this also some persistent rain. We used one of the projects we use is the NESD operational blended TPW, and we use this for Europe. And this is a merged product from several sensors and satellites, and it shows us the TPW. That is the integrated amount of water vapor in vertical column and in milliliters. And it's helpful to forecast heavy rain events and floodings, particularly to the coastal countries of the western of the western coast, western coast to the Atlantic. So we have here some values that are above 40 milliliters. So and with these western floods, this was through several days we had this kind of western flux through the coast of Portugal. So I show you the before and the after the event. Up here we have the Meteosat RGB, HRV, for 17th of December before the event and 26th of December, and this is the river Mondego in the center of Portugal, and even in this RGB of Meteosat that has a coarser resolution, we can see that that river Mondego is more visible, so to say, and that it's larger than it appears, and then we can use the MODIS on the satellite Terra for seeing this, and this MODIS satellite has a wide swath of higher than 2,000 kilometers, and it circles the world, and it has 1 or 2 days to see the same point in the world, and a better resolution. So some bands have 250 meters, others have 1 kilometer, and here you can see the river prior to this event and after this event with the flood and because of the excessive rain. Now looking at ASCAT and seeing a new, just to remember a bit, it's a microwave radar instrument. It operates on satellite METOP, and it derives wind speed over water, measuring the roughness of the water. It has 2 slots of 550 kilometers. We acquired the data 30 minutes to 2 hours prior to the acquisition of the data, and above 30 meters per second, it has difficult to measure the winds, and it has global coverage. So some of the advantages of the ASCAT, it's the identification of some synoptic features, improving the surface analysis we do in our services, like frontal wind discontinuity, low centers, locations of high pressures and significant wind areas. Also, it helps on detection the mesoscale features, like some downbursts generated by convective environments, land breezes. And it also helps wind warning improvement in sea forecasting, like if you need to initiate the wind forecast that it wasn't the wind warning that wasn't forecasted by the model, or terminate it, or even validate the wind warnings with the ASCAT. Some of these advantages are the ambiguity, and also what I said before, like the above storm force in buffer scale winds sensitivity, and when we have land and ice and rain contamination, despite ASCAT is using the C-band and rain contamination is not such a problem, but in over land and over ice we don't have ASCAT data. You can use the KNMI multi-platform product. It has global coverage. You can click it and access the ASCAT data. Also other data from other satellites like the Indian satellite SCATSat, SFOSat, it's a Chinese and French satellite, and the Chinese satellite HI-2B. And then it appears a window. You can overlook the plot, and it shows. Looking at the colors, you can see also the more intense areas of the of the observation of scatterometers. So then it will open a window. On top there's the identification of the scatterometer, ASCAT-B in this case, the date, the hour, and the channel of the image, of the infrared image used to superimpose the ASCAT data. Sometimes it's Meteosat or GOES, Himawari. It depends on the place we are. And then we have the half barb. It's like 2.5 meters per second. One full barb, it's 5 meters per second, and dependent, it's 25 meters per second. And in here we have the exact acquisition time plotted next to the satellite swath. Winds here are colored by the Beaufort scale. You can see it below here. So 6 is a near gale, 7 it's gale, 8 strong gale, and 9 storm. So above these, they have extreme sensitivity to these wind forces. But until the 9 in Beaufort scale, it has a high reliability on wind strength. Also, we have the MLE values, but usually indicate high spatial wind variability or rain presence in the wind vector cell. It's mainly used to detect lows, fronts, downbursts, and aid in ambiguity removal. If you want to see, the KNMI is like 22 hours prior to the near real time, and here you can see the archive data, where you can see the data from all scatterometers, namely ASCAT-A, B, and C, and also other ones from the past. It's also a clickable map, and but we have the separated scatterometer data, not like KNMI, where we have all data from all scatterometers on the same image. Here you have to click by scatterometer. So some special features identified by scatterometer, like gap winds and wind tunneling. I'll show some after. Wind tunneling, coastal jet, onshore storm force fields, tropical cyclone analysis, and relation with SST gradients and currents. This one I won't talk about, also not the tropical cyclone analysis, but it has been proved that when we have gradients of sea surface temperature, we can observe some higher winds on the warmer side and calmer winds on the cold side. So looking at some tunneling winds here in the Adriatic Sea. This is Italy, and this is the Adriatic Sea. On the 19th of November 2019, we had the Venice flooding. It was a third major flood in less than 1 week, and the peaks of the flood were underestimated. So we had the models predicting lesser winds than it was observed. You can see a passage of ASCAT, and here you can see the difference between the ASCAT and the GFS, and you can see that was underestimated, particularly this area here with so the floods were higher than expected during this time. Here you can see a passage over a convection zone, and you can see the convection downbursts appearing in the ASCAT. It would be a major advantage if we have superimposed satellite image, which I haven't here, but it is confirmed that this area had some convection, and you can see the difference between the calmer winds south. And these winds, it's like spraying with the downbursts arriving at the surface of the sea. Like coastal jet, during the summer we have in Portugal western coast north wind, very intense. It's mainly generated by the pressure gradient between high pressure zone at the western of the Portugal and the low thermal, and it appears also in the scatterometer here. We had some some values near the coast ranging 25 knots. About funneling of winds, also Ângela already talked about the 20th of January, 31st of January. So we had the funneling of winds between Corsica and Sardinia. We can see some of these here. Of course, we have these magenta markers that denote the land presence, but the winds we can see here passing through the both islands. And this is the funneling here. This is the 12.5 kilometers resolution. You can also access it through the KNMI site, and it's compared to the blue arrows that are ELM model, so with a coarser resolution than the ASCAT. So it's very good to access the ASCAT in these conditions. Also, during this time, we had the onshore near storm force field here at the Balearic Islands, and we had 30 to 40 knots, and there are several images and videos on the net that can show what this storm surge by the intense wind and persistence through these days had on the shores of the Balearic Islands and the eastern coast of Spain. Here you can see the altimeter data. Also, you can access it through this Manitas star site we've seen before, and this is in feet the significant wave height, and we have values here through 20 to 26 meters. This is the if you don't acknowledge this area, this is the southeastern part of Spain. Like the Balearic Islands are around here, and this is Corsica and Sardinia. And you can see values through 20 to 26 feet. It's like 6 to 8 meters of significant wave height that concurs with the values Ângela showed before of the buoy from Valencia. We have a here 32 value. It's clear contaminated by or probably contaminated by land is this value here, but mostly of them are through 20 to 26 feet. Here you have the same graphic Ângela showed us before. On the 20 and 21, we have significant wave heights near around or up higher than 8 meters. Of significant wave height, so record-breaking values for the Western Mediterranean Sea. Looking at some cyanotic features, we have a passage of the ASCAT through a low in the Pacific Ocean, and you can see very well the center and some storm force winds. And if you look it through, I went through and looked for the Mawari image. It's a very beautiful image with a RGB Hermes from EUMeTrain used with the new channels of the EUMeTrain Mawari 8, and you can access it. You can access it through this site here if you want to see it. You can see the GOES, the new GOES images. You can see also Meteosat images. You can see Mawari image with the new resolution, like 10 minutes. You can have a mesoscale resolution, a very good resolution over some areas. It's a site worth seeing. And since we were talking about ASCAT, just to talk a little bit about the future of ASCAT for the next EUMETS polar system, the second generation. Some differences from the ASCAT will be a doubled horizontal resolution that will provide oceanic wind vectors closer to coastlines. So it will enhance the spatial coverage. The swath will increase from 550 to 660, so a larger area, and you'll have the addition of cross-polarization measurements that will benefit the observation of stronger winds. That's all. Thank you very much for listening.